Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on polymer testing. This is part 3 of a 5-part series we're calling Chase Plastics 101. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your busy day to attend. I have a few housekeeping items to go over before we get started. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you would rather ask your question verbally, please raise your hand using the react icon in the toolbar, and I will unmute you and call on you to ask your question out loud. We will answer all questions at the end of the webinar, so stay tuned. You can access and download PDF copies of Andrea's presentation, our product line card, common processing guide that she will be referring to, and information on our technical engineering team in the materials section during the presentation. You can only download these during the presentation. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of her presentation and the handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to our presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted, including links for this 5-part series called Chase Plastics 101, where we will discuss polymer basics, modification, testing, fabrication, and common polymers. You can register for Part 4 on Polymer Fabrication 101, that's coming up on August 27th, and Part 5 on Common Polymers 101, that's coming up on September 24th now. Those are live on the website. You can also watch Parts 1 and 2, as well as any previous Chase Knowledge webinar from this page at a time that is convenient for you. You can subscribe or invite your coworkers to subscribe to receive notifications on all future Chase the Knowledge webinars by clicking that button in the right-hand section that says subscribe here for webinar notifications. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. In addition to our presenter, Andrea Kendrick, whom I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to answer. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise that she brings to the table. So without further ado, Andrea.
Hey, good afternoon. Andrea Kendrick here. Today we're going to go over polymer testing. This is part 3 of our Chase Plastics 101. Our agenda for today, we're going to go over plastic data sheets. We're going to go over data sheets versus graphs. We're going to talk about some limitations that data sheets have. We're going to go over some property and tests overview, so review some of those property tests. And then we're going to do some comparison across a few polymers that would help get an idea of where some of those values might fall. So a plastic data sheet, also known as a technical data sheet, TDS. So further in this presentation, you'll likely see that I reference TDS as the acronym there when we're going through it. Data sheets are used as a marketing tool. They're to help give you a snapshot of performance of a material. And so it gives you a nice coarse comparison if you're trying to look at different resins, different grades of the same resin, different filler content, you name it. It gives you a different comparison so you can look at it and get a quick snapshot of its performance. The thing to note is going to be that these data sheets are going to be a distinct set of conditions and variables. So it's one condition, one variable. They might give you multiple different ones, maybe different temperatures, different loads, whatever it may be, but it's one value based on those particular conditions. Now to compare, if we were to look at a data sheet versus looking at a graph, which a lot of engineers will ask for so they can compare, data sheets again, snapshot of your properties, one distinct set of variables. Graphs, on the other hand, allow you to see a response in changing conditions. So on the graph, you can see over to the right, you see your stress versus your strain. So crossed as it's being tested and it's being strained or elongated, you can see the changing stress required there. What's nice about your graphs is you're not limited to one set of conditions. So in the case of, if you're looking at this particular material and you're like, what does my strain look like at 10,000 PSI stress? Maybe that has something to do with your design. Maybe you need that information. The data sheet's likely to give you a yield and a break value, which I've also highlighted, break. It's not going to give you something like that exact stress, where you can find it in a graph. So the graph allows you to look inside to find values as it changes, as well as to predict what will happen past the data values that are shown on your graph. Of course, on this one being stress versus strain, after it breaks, there's no more values. The material is broken. But in some cases, depending on the graph, it allows you to continue on and extrapolate data and see where it will fall. So a few additional examples. There's kind of a lot, and a couple of the graphs are kind of small, but just to give an idea of some additional graphs that you might have heard of, heard referenced or seen, and they give you different values. So on the top, you can see stress versus strain and at different temperatures. So you can see it at room temperature, so your 23 C, you can see it at 40 degrees C, and then 100 degrees C. So if your application is something that might be in an environment that will see 40 degrees C, your tensile strain and stress at room temperature or lab conditions aren't going to give you the values that you're going to need at the temperature your part's going to see. And so something like a graph could potentially provide that additional information for you. Then I've also included a viscosity versus shear rate graph, a modulus versus temperature graph, and then another stress versus strain graph. So again, bottom one's maybe a little hard to see, but an additional resource and some more graphs to look at that you might be able to be provided on the material that would give you more information. Okay, so some limitations on data sheets that I want to make sure that we're considering. So there's things that data sheets don't typically account for that will affect how the property performance will be or how the material will perform. So things like chemical exposure. So if it's exposed to a certain chemical, certain time period, you name it, if it's exposed to it, whatever the property test you're looking at comparing, it's likely to not perform the same as what the data sheet says it will, because that's not being exposed to that chemical. Thermal exposure, UV exposure, if it's outside, if it's someplace where it gets really hot, again, the data sheet doesn't account for that. It just gives you lab conditions. Then you have humidity, part design, and processing. So if the part design maybe has a sharp corner, so there's extra stress in that area, not going to perform as well. And then processing, maybe you processed it, while it was still wet instead of drying. Well, now we have more stress or more potential degradation, and it will not perform the same as you'd expect it to based on data sheet values. So I have a couple examples of that. So chemical exposure. So this would be taking a TPV and we expose it to ASTM oil 3 for a day at room temperature, and then diesel fuel for 3 days, also at room temperature. And so you can take your standard data sheet value, which came in at a 5.3 MPa. This is for the 65 Shore TPV. Once it had been exposed to ASTM oil 3, it dropped to 4.6, and then diesel fuel 3.4. So this would be an example of the chemical exposure and how it can affect those properties. And none of this information would be on a data sheet. It would be provided separately. But again, something to consider. There are some limitations there. We don't know about that exposure. Another example would be temperature and humidity. This one happens to be on a nylon 4-6. So if you look at a data sheet at standard lab, room temperature, dry as molded, not conditioned, 100 MPa for tensile stress. When it moves to 100 degrees C, that value drops to 55. When it goes to 200 degrees C, that value drops again to 30 MPa. And then if we go back to room temperature, so the same as the 100, but we condition it so it's been exposed to moisture, it drops to 55 as well. And so you can see our data sheet might only give us the 100 MPa value, but if it's exposed to temperature or humidity, those values and performance is going to drop, but a data sheet might not capture that or show that to you. And then the final example, I have a 85 Shore A TPU, ester-based, and same tensile stress performance, but after UV exposure. So the datasheet value puts it at about a 40 MPa. After 500 hours of UV exposure, drops to a 26. Then it drops to a 19.4 after 1,000, and all the way down to a 4.9 after 2,000 hours of UV exposure. Again, datasheet will show you about that 40 MPa. It will not show you any of those other values. So if you're making a part out of an ester-based 85 Shore A TPU, and it's going to go outside and it's going to see UV, it's not going to perform at the 40 MPa. It's going to start performing, depending on how long it is outside, closer to your 26, 19, or 4 MPa. Okay, so now we talked about some of the limitations, data sheets versus graphs. Now let's talk about the data sheet itself and some of the data that you will find on it. So typically when you're looking at a data sheet, at this time, if you guys have the ability to do it, open a data sheet for a material you're working on. That would be most convenient to do. But you'll notice that they then categorize each of the tests typically into a handful of different categories: physical, mechanical, impact, thermal, electrical, flammability, and optical. Those are going to be your most common ones, where they'll group all the different tests under those. You'll see hardness is also on there, and I didn't call it out. There are a few other ones that are not as common, but might also be found on a data sheet. So we'll group those in here, and then we're going to go over a few of the tests under each category, what that test is, what it means, and then some examples. Okay, so our physical property tests under this would be specific gravity. Again, if you happen to have a data sheet open in front of you, perfect. You can look at the specific gravity of the material you're working with. Each of these pages, as I described the different tests, are going to have the test methods, the standard ASTM and ISO, or UL when we get to RTI, units for how they will report that test value, and then a little more information on it. So in this case, specific gravity, units are going to be grams per centimeter cubed. These are going to be your typical units as well. There are some other ones, they're just not as common, so I'm going to give you your common units for it. Grams per centimeter cubed. Specific gravity is the ratio essentially of the material compared to the density of water. And so in some cases, if you're looking at certain data sheets, they'll just refer to it as density, but do know that it's specific gravity because they're comparing that material's density to the density of water. So because we compare it to water, if it is less than 1 gram per centimeter cubed, it's going to float. It weighs less than water, it will float. If it is greater than 1, it will sink. So we have a handful of materials that have specific gravities under 1, they will float. Propylene, ethylene, unfilled, they are less than 1, they will float. The vast majority of our other materials, though, are above a 1 and they will sink. So, and part of the reason, or another good reason we want to know this, is because with consistent volumes for parts, so your part volume when you design it is based on that volume, different resins with their different specific gravities are going to cause the part to weigh more or less. And I have an example of why that might be important as well. So because we sell plastic per pound or kg, when you have parts that are, when you have materials that are lighter, you can make more parts out of the material that you buy. So an example of that would be if we know that our part is 100 centimeters cubed, just an example, we're making it up, and we know the specific gravity of an ABS is about 1.05. The specific gravity of the propylene for this example is 0.902. So if I took a 55-pound bag of material that I buy, I can make approximately 237 ABS parts, but I can make 276 propylene parts. So if you're comparing, ABS and propylene are a good little bit different, so maybe we're not comparing those two materials too often. But if you're looking at a couple materials and you're trying to decide which one is going to be best for your application, which one you're looking to purchase, looking at the specific gravity, if there is a difference, it could make a difference. If you're able to make more parts, but maybe the material is a little more expensive, maybe it nets out to be the same. So something to consider when we're looking at our materials and we're looking to pick a material for application. Okay, so next one under physical properties is going to be shrinkage. It's not always on the data sheet. Sometimes you'll have to get with the manufacturer or distributor, us, to get those values or those guidelines for the material. But when they are on a data sheet, they're going to be given typically in inch per inch or percentage. You can compare them. They are ratio, so you move the decimal over to get the percentage. So shrinkage is an important thing that we need to know about because it is the difference between the actual mold dimensions and what the molded part comes out as, because plastic materials will contract when they are cooled. So they shrink. So they will not mimic the exact dimensions of your tool. They'll shrink a little bit and be a little bit smaller. So all plastics shrink, but they do not all shrink the same amount. So semi-crystalline materials, nylon, propylene, PBT, they're going to shrink more. They expand more. If you listened into the first part, the first Chase Plastics 101 on basics, we went over semi-crystalline versus amorphous. Our semi-crystalline materials will shrink more compared to our amorphous materials like an ABS or a polycarbonate. One thing to note that I always want to point out is that the data sheets or guidelines given for shrinkage are good guidelines, but do note that your gate location, your geometry, the amount of gates you have, your part dimensions, and how you process it all can affect the felt shrink of the material. So we give a good guideline, but it's not guaranteed it's going to be that exact value every time because there are a few things that can affect it. So do keep that in mind. And this is where I reference our common processing guide. So if you don't have it already, it is available in the material section to download. But if you look at the furthest column all the way to the right, we have mold shrinkage called out. So you can see the top box has ABS, FRABS, and ASA, all amorphous materials. You can see 4 to 7 thou inch per inch shrinkage called out. And then the box further down has a few different nylon materials. So you can see those are in the range of 1 to 2.2% or 10 to 22 thou. So a little different within the two different or the different nylons, but a good difference in your shrinkage. So we want to make sure we're understanding the shrink values. Your tool makers are certainly going to need to know that when they go to make it, but you do have quite a bit of difference in shrink between the different types of materials. Okay, and then I believe the last one for physical properties that I'm going to cover is going to be your melt flow or your melt volume rate. So this is the extrusion rate at which the resin will come through the orifice of a tester. And then typically if you're doing your melt flow rate, it's going to be your grams per 10 minutes. So how much came out in 10 minutes, or it'll be cubic centimeters per 10 minutes. So how much was displaced. And I have a picture of that on the next slide. But some things to note here are going to be that we can use this to differentiate between the same material. We can look at the melt flow for similar materials. So I can compare a 10 melt ABS to a 20 melt ABS. We do not compare our melts, and I'll show why in a few slides, but we do not compare melt flows across different materials. A 10 melt ABS will not be the same as a 10 melt polycarbonate. Again, I'll show some data in a couple slides. The other thing to note is that melt flow and melt volume rate tests are highly affected by moisture and filler and reinforcements. So certain materials that are very sensitive to picking up a lot of moisture, like your nylons or your polyesters, they're unlikely to have melt flow data because, again, it is very affected by moisture. So within the same lot of material, if you take it at a 0.05% moisture and a 0.2% moisture, you'll have a large difference in melt flow that will be shown because it is so affected by moisture. And then lastly, which will also include the data for it, melt flow and melt volume rates are low shear tests. There's not a lot of shear going on. It's just the weight of the load that's put on there. And again, show that a little bit. And so it's not necessarily indicative of your actual performance at your high shear injection molding processing conditions. Again, I'll show a little bit of data as well. Okay, so if we're looking at it, this is going to be your melt flow tester up in the top left. And then you look next to it, it's kind of a drawing version of it. And so each different polymer has a specific condition or conditions that are common when you do melt flow testing. So in the case of something like a polypropylene, it's common to see it tested at 230 degrees C and 2.16 kg. So that would be your temperature and your load. And then we talked about melt volume rate. It's the amount of volume, cubic centimeters, displaced during the test. So if you look over here where I've highlighted, it will take the volume of how much has been moved in this apparatus per 10 minutes. So an example could be 10 cubic centimeters per 10 minutes. That's how much was displaced. Then your melt flow rate is going to be your weight. So how much the material comes out, we weigh it, how much came out in 10 minutes. So 10 grams per 10 minutes. Okay. And then as promised, there's a lot going on the slide, so I do apologize for that, but it is important to note it. So I repeat, low shear test, not indicative of performance at higher shear conditions, so at injection molding conditions. Because plastics experience different levels of shear thinning at injection molding shear rates, we cannot compare dissimilar materials. So the example here would show, if you look at ABS, over here on the left-hand side, where we're pointing here, at the lower temperature, you can see the viscosity is higher than the polycarbonate. So if we were to look on a data sheet, it would show that this ABS had a lower melt flow than the polycarbonate would. Then we move over to the shear condition for injection molding. You can see that they flipped. The ABS has shear thinned more, and it has a lower viscosity now than the polycarbonate. It is flowing easier and better than the polycarbonate is. And so although on a data sheet, maybe one says 10, one says 20, what they actually experienced during injection molding has now changed because they are two different materials that shear thin differently. Okay, this is why we don't compare dissimilar materials. We don't compare their melt flows. Okay. All right, so now we'll get into some mechanical property testing. We'll start with tensile strength. So this is going to be the maximum amount of load it can withstand before breaking. I do want to note, I don't include flex strength in here. Just know that it's similar, just in a different type of load. So tensile load is if you are trying to pull it apart in opposite directions. I have a picture of an Instron machine showing that. It's also referred to as tensile stress. So in some of the charts or some of the information or data sheets, it might say tensile stress instead of tensile strength. They mean the same thing. There's a few different places to which it can be tested to or reported as. It's typically done to break, where it completely breaks apart, or it can be tested to yield, which essentially means I get to a point where I've deformed it permanently, it will not snap back, or ultimate strength, which is the absolute highest stress it will support before failing. Okay. And then I'll go over elongation, and then I have a couple pictures to kind of show what that testing looks like. So tensile elongation, also known as tensile strain. It's the difference or change in size versus the original size of the material. So how much does it elongate when I'm pulling it apart? So an example, to use this in an application that might be easy to understand, if you take paper and you try to pull it in opposite directions, it's not going to stretch very far before it tears. Versus if you take a Laffy Taffy, the candy, and you try to pull it apart, it's going to stretch a lot before it breaks. So your taffy would have a really high elongation, your paper would have a really low elongation. Okay, so now the test and kind of what that looks like. So you can see kind of it looks like a reddish part in here. What's going to happen is the machine's going to pull it in the opposite direction while this stays stable. And so the tensile strength is going to be how much load as it pulls apart it can withstand. And then the elongation is going to be how far does it stretch before it breaks or before it yields. Okay. And then on a graph, if you've seen a tensile stress strain graph, what it would look like is something like this. Your yield point is going to be right here, where you don't see an increase in your stress as you continue to pull. So this is your yield point they're at different temperatures, I believe. So here, and then your break where it finally breaks apart, and there's no more value to be given. You broke the part. So stress strain curve, what it looks like compared to the actual testing apparatus. Okay. Flexural modulus, again, I mentioned we are skipping flex strength. We also skipped tensile modulus. We have a lot of tests to cover, so but we can go over them separately if need be. So, but flexural modulus, this is going to be by very more scientific definition, the ratio of outer fiber stress to outer fiber strain. What that means is modulus is your resistance to deformation under that particular load. So it's your stiffness essentially. So how stiff is your part? So it gives you an idea of how much force is going to be needed to bend a part. So if you have a really high flex modulus, it is really hard to bend it. So it's going to be a very stiff part versus your lower modulus, which would be a more flexible material, easy to bend. Okay. And then a picture of how they test that. So instead of being pulled apart in opposite directions, your flex testing is going to be pushing down on a supported beam on both sides, and it will take your strength will be how much it can withstand before it breaks, and then your modulus is going to be how stiff it was. So that was your mechanicals. Again, we skipped a couple of them for sake of time and trying to cover a lot of different tests. So now we move on to our impact properties. So in this case, we're going to talk about IZOD impact. And so this is going to be the energy required to break a specimen. And so what happens is a pendulum comes down and hits the material. And I'll show you pictures on the next slide for it. Essentially what it means is the energy that ends up getting lost by the pendulum is absorbed then by your test specimen, and that's how they're able to calculate your impact strength of material. The one thing I'd like to note here is going to be that if you're looking at ASTM testing, it's going to be done based on thickness. So you're going to see foot pounds per inch, so inch being the thickness of your specimen. ISO, however, are done on area. So you'll see typically kilojoules per meter squared. You might also see them in foot pounds per inches squared, but it's area based. So note that your different test specimens also have slightly different dimensions. So there is a way to do kind of an approximate or a rough conversion, but note that if you're looking at something that's giving you a value in foot pounds per inch and foot pounds per inches squared, because of that thickness versus area, you're not looking at the same values. So if you're looking at the foot pound per inch squared, you're like, wow, this value is so high. Well, yeah, there's an additional variable in there. So keep that in mind, and we can do rough conversions. So if you're trying to compare some materials, we can certainly help with that. But do note that they are different. Please note that on the data sheet. So some pictures. So if you look over here on the right-hand side, this is going to be your plastic piece here. And you can see the little notch on it. So there are cases where you'll have notched IZOD impact, which is the most common. And then sometimes if you're looking at a data sheet, you might also see unnotched IZOD impact, meaning they did not cut out that little triangular notch into the material. The notch allows it to break across it. It basically makes a spot for you to propagate your break. It makes it more uniform, or at least the site at which it breaks is more uniform. So we tend to use notched IZOD as a more uniform value to compare. And so your pendulum starts up here, it comes down, and it breaks the part, unless it's a no break, in which case then it doesn't break. But breaks the part, and it measures how much the energy was absorbed and gives you your IZOD impact value. So I don't have an entire page with test methods and everything for Sharpie, but Sharpie is another impact test as well. So similar concept, you have the pendulum swing coming down. What really makes the difference is how your test specimen is being held. So instead of being held upright, this is being held on both sides, and the notch in this case faces away from where the pendulum comes down and hits it. And so it'll come down and hit it as it is facing or laying down horizontal and hits it that way. The other thing to note here is going to be that because it's being held differently, there's no way really to completely convert. So if you give me a Sharpie value, I can't convert that into an IZOD value. They generally go hand in hand. If your IZOD values of a material are getting higher, you have a higher impact, higher IZOD value, your Sharpies are going to be higher. But I couldn't take a 5 foot-pound per inch Sharpie and go, yes, that's a 4 foot-pound per inch IZOD. You cannot convert them. So if you're comparing a couple materials, you want to make sure that you have the same impact value, same impact test being done, so you can compare them apples to apples. Okay, so now we're talking some thermal performance a little bit. So we're talking about heat deflection temperature. Note there are other ones. There's VICAT and some other stuff that falls under there, CLTE, a few other tests as well that I'm not going to cover, but can certainly answer any questions that you might have about it. But for this presentation, heat deflection temperature, this is going to be the temperature at which your specimen deflects, 10 thou of an inch, and that will read the temperature as soon as it deflects that. It's done at two common different loadings, either 66 or 264 PSI. There are some other ones where they might use different loadings. Those two are your most common. You might also see on a data sheet that they'll refer to it as deflection temperature under load, DTUL. These tests mean the same thing. Not to be confused though with VICAT, that is slightly different. So, but your deflection temperature, it gives you a quick little short-term heat resistant performance. And so it gives you an idea of kind of where you'll start to see some deflection or some movement in your material based on those temperatures. So some pictures, quite a few pictures on this one. So in this case, you're looking at, this would be your tensile bar here. In this case, the way that they're testing it is actually would be edgewise because it's sitting on the edge instead of flat. But your load is pushing down, which would be this right here. So this would be what would be your 66 or 264 PSI load. It's pushing down, and then you have a gauge. So as soon as it deflects, it hits, and then it takes the temperature of the oil that it's in. And they slowly raise the oil. They have a standard for doing it, a certain little bit at a time. And then when it finally hits a hot enough temperature, your material will deflect. It'll take that temperature. And then this picture up here is what an actual machine would look like. So you'd have your loads up here. Most of the time you can't see much of it because it's inside an oil bath, so it's hard to actually see the testing that's going on, but this is what is happening when you're doing your HDT testing for short-term heat performance. Okay, another heat test that you will find is going to be relative thermal index, or RTI. This is a UL test, so instead of having an ASTM or standard ISO method for it, this is done through UL. So they do UL 746B for this test. It's done in degrees Celsius. This particular test is a little more long-term. Not a little more, it's a lot more long-term. It's an indication of how well it retains its properties, physical, electrical impact over an extended period of time. That extended period of time is 100,000 hours. As long as the material maintains or retains 50% of its original electrical, mechanical, and impact test value, that is a temperature at which the RTI is set. So in the case of your high temperature materials, the RTI is 150 degrees C. It means that the expectation is that for 100,000 hours, it can sit at 150 degrees C. And when you go to test your mechanical, electrical, and impact testing afterwards, it's at least 50% of its original value after being exposed to the temperatures. The other thing is that based on chemical structure, if the supplier doesn't want to have RTI tested, based on its chemical structure, based on its chemistry, based on what material it is, it can be given a generic thermal index value. And so you might see some yellow cards if you're looking at UL yellow cards for these values. You might see that they have the generic value listed. It just means that they didn't necessarily test it, but based on that chemistry of that material, that's what it had received. So if we look at that graph, or that chart, excuse me, of those values, if it's a nylon, they give it a generic value of 65 degrees C, all the way down to, if it's a PPS, they give it a 130 degrees C. And what you'll find is when they actually test the material, it generally tests quite a bit hotter than the given value. So the couple examples I provided would be just a standard Ultem PEI grade. So if you look at that, it tests at 170 for almost all of the thicknesses. You can see at the 0.4 millimeter thickness up here, you can see 105. I'm guessing they didn't actually test RTI at that thickness. That's why they received the 105. But all of your other thicknesses you can see tested at 170. And the generic value is the 105. And then similar to down here, this is a PPS. Its generic value is 130. So you can see at the really thin section, it tested at 130. Again, I'm thinking they probably didn't have it tested at that thickness. And then all other thicknesses tested at the 220, 200, and 220 degree temperature. So quite a bit hotter than the generic value it was given. So that's pretty hot there. But it's an okay temperature to use as a long-term heat performance to show your material and how it will perform. Okay, so the last few slides I went through, so I talked about the property test, which is all fine and dandy, but if there's certain materials that you haven't worked with or certain tests that you've not heard of or used or looked at, what does all of that mean if we don't have a few data values to show what that looks like or what those values end up being? So I have a couple slides comparing a couple different materials, and then I have a bunch of graphs to show some generic values for some general purpose materials as well. So we'll go through those. So for this particular one, I took a general purpose unfilled polycarbonate and a general purpose unfilled ABS. Now, do note, as we go through the values, there are different types of PCs. I could do a really high flow PC, which would dramatically lower its impact. I could do a high impact ABS, which would, as the name would suggest, give you a high impact ABS, or a high heat ABS, which would then lower its impact. So there's a few different ways of doing it. This is just what we would consider maybe just like a good generic PC and ABS. So if we're looking at the diagram, I then also compared with the actual values. So our specific gravity here for the materials, 1.2, 1.04. So you can see the ABS is lighter. We'll be able to make more parts out of the ABS if we were trying to decide between the two materials. Your tensile strength, you can see that the polycarbonate is a little bit higher, about 9,000 psi versus 6,500 for the ABS. But the ABS is a little bit stiffer, so 355 ksi compared to 339. It's a little bit stiffer, but not quite as strong out of this particular ABS. Then you look at your impact. Polycarbonate is more than double the impact of this particular ABS. So a 13 foot-pounds per inch compared to a 6.1. So good impact out of the polycarbonate, which is one of the properties it's known for. It's known for its really excellent toughness and impact. So makes sense that it would do well there. And then you look at your temperature performance. You're at about 300 versus about 200. So your polycarbonate also has the advantage there. One thing to note here would be if I took a PC ABS, I took an alloy out of the two, what you can imagine is that the values would end up somewhere between all of them. And so the polycarbonate would end up being a little bit lighter because it'd have the ABS in there, and you'd get a little bit stiffer material. You'd lower the impact a little bit, but what's not shown on the data sheet necessarily you'd get a little bit better low temperature impact with the ABS. So one of those things that maybe it just doesn't show you on a data sheet, right? So good comparison between a PC and an ABS, some general purpose amorphous materials. Then I have one on PBT and one on PEEK. So a little bit of a stretch looking at a PBT as just a real good engineering product versus what we'd consider a little more specialty, a little more niche product like the PEEK. They're both 30 glass filled, so you can see these values are going to be a good little bit higher than your PC and your ABS, specifically because they are glass filled. And we know if we listen to the last presentation, glass adds to your stiffness and strength. So if we're looking at the PBT 30 glass, we're at a 1.54 and a 1.53 for PEEK. So very comparable for your densities. So not much of a difference or savings or anything there. Then we're looking at your tensile strength. You can see that your PEEK is quite a bit higher. It's a little bit stronger than the PBT is going to be at 25,000 compared to 18,000. Then we move to flex modulus. PEEK is also stiffer than your PBT is going to be. So 1.5 million compared to 1.2 million. So again, the advantage in that case, stiffness and strength, goes to PEEK. And your impact, comparable. So impact in this case is going to be pretty heavily dictated by the glass that's in it. It's going to affect that. And so you're at a 1.4 to 1.3 notched IZOD impact foot-pounds per inch. So real comparable. So you're not getting much or losing much in terms of your impact. And then your temperature is going to be a huge shining difference because hopefully we know that PEEK is a high temperature material. So you're looking at a 600 DTUL or HDT compared to a 400 out of the PBT. So good difference there when we're comparing it. So this would be your comparison between a couple of semicrystalline materials. Okay, So I want to preface these next few slides. So there's a lot going on. So I picked 8 different materials. They're across the engineering and specialty products, and they're across 4 semicrystalline and 4 amorphous resins. You'll see that distinction very clearly on the next slide when I go over shrinkage. So these are general purpose grades, what we maybe consider general purpose grades. And this is all information pulled from their data sheets to show their performance. And all unfilled, by the way. So these are unfilled grades, and this is where their different values across the main ones that we discussed are going to be. So specific gravity or density, we range from a 1.04 of the ABS up to the 1.41 being the heaviest with acetal. For unfilled grades, acetal kind of takes the trophy, if you will, for the highest specific gravity. It's a very heavy product at 1.41. And then the rest fall in between that. So between the 1.1-ish to 1.3-ish. It's very common for a lot to fall in there. You'll notice that the materials I didn't pick any commodity grades. So stuff like a propylene or an ethylene unfilled, they'd be under 1. Their values would be lower. But for the engineering and specialty grades that I selected, you can see between 1.04 to 1.4. Okay, so now we can maybe visually see quite a difference in our different materials. So for shrinkage, again, please note different things, how many gates you have, your geometry, how you process it will all affect that. But knowing what we know and what our guidelines would be for this, you can see across the board, all of the materials that are in the 0.5, 6, and 0.7 range, those are your amorphous resins. So if you didn't know that those were the amorphous materials, they are ABS, PC, PEI, and PPSU. Those are going to be your amorphous materials. And then the ones with your higher shrinkage values, semicrystalline, they shrink more. So we have a nylon 6, a nylon 6,6, a PEEK, and an acetal. And so you can see different shrinkage all the way across the board with 6,6 and acetal shrinking the most at unfilled 2% shrinkage. Okay. So big distinction there, big difference there. A decent little spread also for our tensile strength. Again, remember these are unfilled. So if you wanted to affect your strength and then on the next slide your stiffness, you could add glass or mineral to affect that. But for unfilled materials, we're ranging from the lowest being your ABS at 6,500 PSI all the way up to your PEI at 16,000. So you have PEEK is kind of trying to run there behind it, but for the most part, for a unfilled product, your PEI of the materials I selected, really high, really good strength performance. And then your flex modulus. So again, modulus being your stiffness, how hard it would be to bend, something like that. You're going to look at your PEEK takes this one. It's a little bit stiffer than your PEI, but your PEI is still up there. It's a very stiff material. ABS that was not, had the lowest strength. It does not have the lowest stiffness. Polycarbonate and PPSU are tied for the lowest stiffness of all the products, but all within a decent range between 339 and 537 thousand PSI or KS in this case. So a good little spread, but all kind of within a decent range with one another. What we're going to see though on the next slide is where we're going to see a real big difference between our materials when we're comparing them. So data sheet values for IZOD impact, drastic difference. So you can see that polycarbonate and PPSU, they are known for their impact. And so you can see that at 13 foot-pounds per inch, they're the shining stars on their data sheet for impact. And then your ABS, this general purpose one, is at a 6.4. They do make other versions, of course, that would be in different values. We have a high impact grade that gets up into the 8s. And then the other thing to note too is your standard non-impact modified nylon grades, their impact is not that high. But if we took a 6.6 or a 6 and we made it super tough by impact modifying it, those values shoot up dramatically. But this, again, just unfilled standard grades. They don't have any of that in there. So a lot lower value. And then the other thing I do want to note, because it's hard to see on a data sheet value, as we talked about, our limitations, a lot of these materials have practical impact. So when you design it with a good radius and it has a good design to it, these materials aren't going to shatter when you drop them on the ground. That's not how they're going to perform. Though if you look at, a 1 impact compared to a 13, maybe that's what you might think. But it's not what will happen. They're just not as tough or durable as your polycarbonate or your PPSU would be. Okay. And then another decent range is going to be your heat performance because we're comparing engineering versus high temperature specialty products. So you can see that there's a decent range for your temperature. So you have your 6 at the lowest at 140 HDT. And mind you, this HDT is the higher loading, 264. And so being that it's an unfilled grade, all these are unfilled grades, their performance is quite a bit lower because it's got a heavier load on it. So your 6 at the lowest at 140, and then we jump all the way up to PPSU at 405, which makes sense because it would be the highest TG material of all of these. So a good spread on this one as well. You can see your high temperature specialty products, PEAK, PEI, PPSU, are in the 300 plus up to 400 degrees. And then your engineering products are in the 100 to 260-ish for polycarbonate. So a good spread again on this one as well. But just to give you an idea of where some of your performance may be. Also to note, again, I mentioned engineering and specialty products. If you were to put in commodity materials into here, it would throw and give you a bunch of different values to look at as well. You'd end up with lower temperatures, probably some good impacts depending on which type of propylene you use. Maybe use a no-break copolymer. That'll have a really high impact versus using like a homopolymer, low impact. So values all over the place, but just wanted to give an idea of maybe some of the common materials you might use or have used, ABS versus nylons versus polycarbonates, to show where some of these values, when we talk about our datasheet values, where those tend to fall. So just wanted to give a visual to that so you guys can kind of see where that's all at. But again, all of this information available on datasheets, except for the graphs, of course, but all of this additional information available on datasheets so you can compare your materials and figure out what makes most sense for your application and what you're trying to do. Okay. And with that, that is what I had for you guys today.
Awesome job. Thank you, Andrea, for your comprehensive presentation as always. Thanks for the love, you guys. Give it up for Andrea. At this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone. We do have Jason Merkel, who is our technical manager, on hand to assist Andrea with questions today. As a reminder, as you type your questions, please remember to complete the survey at the end of this webinar. Your responses will help shape future Chase the Knowledge webinars, and we always welcome your feedback. Also, be sure to check out our webinars page at chaseplastics.com/webinars for past webinar recordings and future webinar announcements. It's also where you can register for any future Chase the Knowledge webinars, including the next 2 parts of this series. If you would like to have a custom Chase the Knowledge topic presented to your organization, once again, please reach out to Andrea or myself and we can help get that set up for you. So Jason, at this time, it looks like we have quite a few questions, so I'll hand it over to you to get through those with Andrea.
Sounds good. Thanks, Sherry. All right, Andrea, first question. Would you expect a typical data sheet to be exaggerated, more exaggerated? For example, if we were to test a resin compared to data sheet properties, would the actual test results tend to be higher or lower?
So for data sheets, it's a good question actually, because I didn't actually talk about it. Data sheets should be based around typical values, meaning when you go to test it, it should typically fall around those values. Not to be confused with what would be considered quality control minimums or tolerancing for those properties. But when you go to test it, the expectation would be that it should fall very close to what your data sheet is giving you. Then our minimums or our QC, when our suppliers test their lot to lot, those values or those accepted values will be a little bit lower. But when you go to test it, it should be very similar to what your data sheet is telling you it is.
Yeah, I would agree. I think it's also important to note that, they're not particularly a regulated document. So any producer of material can kind of put what they want on there. We would expect and hope that it's representative data of how a product's actually going to perform. But if we were to compare certification of analysis data for a produced lot of material compared to data sheet across our whole supply base, some would come in, higher maybe than expected on the data sheet, and some might come in lower. And when you get into new materials, new compounds, developmental grades, it goes even further off the beaten path. So take it all with a grain of salt, in my opinion, and lean on, existing actual test data if possible outside of the data sheet. But we still use data sheets often as an indicator. Next question, Andrea. Can you directly compare the ISO impact of this area-based versus ASTM impact that is thickness-based?
You can, because we do know the dimensions of the test bars, and so you can compare them. There's a conversion factor you'd have to use for it, though ideally you would have them tested per the same standard. So unlike IZOD and Sharpie that you cannot compare, you can compare ISO to ASTM in area versus thickness. It becomes a rough conversion is I guess what we would call it, but you can compare it unlike Sharpie versus IZOD.
Yeah, I think the critical function there is knowing exactly what the difference is in area, since ISO methodology especially accepts a number of different notch sizes and such. So you really got to have the specifics of the test method, not just, what may be generically listed on a data sheet. Next question is for temperature testing in an oil bath. You mentioned that they slowly bring up the temperature for testing. Question is, do they wait to see if the whole part comes to temperature internally to ensure that the whole part is at that temperature?
No. So it would take the temperature of the water bath itself. It's not measuring the temperature in the center of the specimen. But because they do it so slowly, it allows time for the specimen to get to that temperature. But the actual thermometer is not testing the part; it's testing the oil temperature.
Yeah, I don't think we typically see a probe or anything on the test specimen, to my knowledge. Can you please review once more what can be gained from knowing the materials, either melt flow rate or melt volume rate on the data sheet?
Yes. Let me scroll back to it too to show it. So within the same material, so ABS to ABS, polycarbonate to polycarbonate, your melt flow can give you an idea of the difference in how it will flow within reason. So if I'm looking at a 20 melt ABS compared to a 40 melt ABS, I know that the 40 melt is going to flow better. When I'm under injection molding shear rates, it's not going to be a 2 times the amount difference like the data sheet might suggest, but I do know that my 40 melt is going to flow easier, have a lower viscosity than the 20 melt is going to be. And so if I'm, using a 20 melt and it's maybe there's too much pressure when I'm trying to fill it, or I have additional cavities that are not getting filled, we can move then to the higher flow. But again, only within the same family. Same as comparing a 20 melt PC to maybe a high flow lens grade of PC that's at a 65 melt. I know that the 65 melt will flow dramatically more than the 20 melt. It won't be the exact 3-ish times amount when it's under this shear of injection molding, but I do know that it will flow a lot easier. So it's good tribal knowledge to know, hey, I ran this particular material, this particular melt of ABS or PC or whatever material you're using, and it wasn't quite doing it. I need a little bit better flow. Maybe my pressure is a little too high. Maybe it wasn't quite filling out. Then I know I can, based on that particular value on a data sheet, move to something with a higher melt flow to achieve that.
I think we can also infer some performance properties on a material based on flow rate, and this isn't equal across all polymer types, but if we were to compare, say we're trying to fill a cavity with an 8 melt polycarbonate and it's not quite full, so we move to an 18 melt or 19 melt, which is standard injection molding grade melt flow rate for polycarbonate, and we get almost full by switching to that, but we're not quite there, so we switch all the way up to a 40 melt, or the really high end, like a 65 melt, right? We could fill the cavity most likely at that point. Pretty hard chance not to, actually, with that high of a melt flow. But part performance will also be affected. This isn't just a processing aid. In order to get significantly higher flow rates, something has to be changing about the polymer, whether that's adding lubricant or processing aids to help it fill more easily to reduce friction, or more often by actually altering the polymer backbone to have less branching or shorter polymer chains or shorter branches at the end of the day. Those changes to the polymer chemistry will also affect the end use performance properties. So rule of thumb is typically the higher you go in melt flow, the lower, mechanical performance you may have. It might take a hit on impact strength or overall tensile strength, or have is even degrade in the barrel to a certain degree more easily than maybe a shorter chain, lower flow molecule would. A longer chain, lower flow molecule would be. So it gives us kind of a gauge, I guess, for molecular weight, which will also ultimately have an influence on properties. Now, those should be reflected in the data sheets, so you would be able to see, before it gets into a press, how they may differ. But in addition to its ability to fill, it will also have an effect on mechanical performance.
And then outside the data sheets too, they might use melt to determine if you've degraded the polymer as well. So outside of use for data sheet, if you take a 20 melt polycarbonate and you run it, you make parts, and then they do a melt flow test and you find that it's a 40 melt now or a 30 melt now, there's likelihood that we've broken up some of those chains during processing. And so it's flowing easier. And so that could be an indication of that. So outside of the data sheet, it is also a useful test in that regard.
Next question, why does ABS have better low temp impact versus polycarbonate?
ABS has butadiene. It's the B in ABS, which is a rubber, has a low TG, so low glass transition temperature that aids in its impact, and specifically its low temperature impact. So same with stuff like TPOs. We take a propylene and we add in a low temperature, low TG rubber to it. Same with nylons. When we impact modify them, the low TG impact allows the molecules to move at those temperatures, the low temperatures, or continue to move, I should say, to allow them to absorb the impact. So ABS, TPOs, anything really that has the rubber in them will allow them for better low temperature impact performance.
Awesome. Next question is, how do I get a copy of shrink rate chart or shrink rate values for TPU?
So we have general values on the Common Processing Guide. It does vary quite a bit, as you can imagine, by your hardness, meaning the hard segment amount versus your soft segment amount will vary. It will also then vary your shrinkage. So if you have a particular TPU in mind with a particular hardness, please do reach out and we could provide something like that. Some of the manufacturers will make a graph that gives, hey, at this hardness, it's around this hardness, it's around this, and so on. So it will vary. Our range on our Common Processing Guide is likely a very large one to kind of capture all of that, but it will be a little more grade specific and hardness specific for TPU.
Next question is, what's the impact of temperature change rate for heat deflection temperature testing, knowing that the rate has some impact to VICAT point as well?
So I think the question revolves around the fact that most of the time for VICAT, they mention the rate of change for temperature versus they don't necessarily mention it when you look at the data on the data sheet for HTT, but there are set standards for the temperature raise and at what rate. And so that would be dictated by the ASTM or ISO method. I couldn't tell you off the top of my head exactly what that is, but I could find the method and look into it. But that will be dictated by the test method being used.
I thought it was just a few degrees Celsius per minute, but I'd have to double check as well.
Mm-hmm.
Let's see here. What's the testing difference for HTT between ASTM and ISO? Do you happen to know off the top of your head, Andrea?
Off the top of my head, I don't. I know your specimen size might be a little different for saying that it's a little bit different for your impact and other tests. But the actual methodology and the procedure for it, I don't know if there's much of a difference.
If there's any specific on that you'd like to see, please feel free to shoot us an email afterwards. We can get you some deeper information on that. This question from someone who hasn't been able to watch the first two sessions of this series, interested in how melt flow can affect, reduced tensile strength. Do we plan to review how additives can improve physical properties, et cetera, or affect other properties as well? I can't remember what's on the horizon, Andrea, for future presentations.
Yes. So great segue or guess backwards into it. The last one that I just did was on polymer modification. And so it reviews glass and mineral and long glass and the effects that it has on the base polymer. So going over increased strength and stiffness, generally a decrease in impact if you're adding glass and temperature. So yeah, that was completely covered on the second one. So please send a note if you'd like us to send that, or as Sherry mentioned on our website, feel free to sign up or have it sent to you and watch it from there. But the second one on polymer modification covers that.
And Dylan, on that, if you have any, specific questions about, a particular additive type or material type or grade of material, obviously we'd welcome that to, take it off the presentation here, but we can discuss separately. We happen to answer any questions you have. Andrea, next question is, what's the better factor for elasticity and flexibility? Is it impact or elongation and break?
For elasticity of the material?
Yeah.
So I guess it kind of depends on what you're trying to compare or what you're trying to determine out of it. They're generally going to go pretty hand in hand. If you find that you have a really high impact material, generally your elongation will follow suit as well. There are some exceptions to that, of course, but they generally go hand in hand. If you're worried about the actual impact of something, you're dropping something, it's going to run into something, we're probably going to care more about the impact. If we're worried about if we can kind of stretch it just a little bit to get it around something, an undercut, an assembly where we have to stretch it around something, maybe we're shoving a thread into it, whatever it may be, elongation is likely a little bit better of a property to look at for that. So it really just depends on what you're trying to do or use that information for. And that would determine what property we'd be looking at.
Yeah, I think, unfortunately, it's not an easy one answer. It depends on how loads are being applied. When we try to look at, tensile testing versus flex testing, for example, where it's parallel with the part geometry versus perpendicular, then I would lean towards elongation, probably over impact. If we look at a product as simple as a, glass-filled polypropylene homopolymer, moving from a 20% glass-filled product to a 30% glass-filled product is going to show a slight increase in impact performance in a lot of cases. We're moving from 10 to 20, you would see the same thing. But knowing that we're adding more glass, we're increasing the modulus of the product. We're increasing the tensile strength. We're increasing the tensile and flexural modulus. So it's not really resulting in a more elastic or flexible product after that. But the impact can still go up with the increase of glass to an inflection point. It will eventually start going back down if you add enough glass. So not really a great rule of thumb, unfortunately, but elongation would show those differences slightly more than impact in that specific scenario.
All right, Jason, that looks like our last question, as far as I can see. So great job, Jason, Andrea. Again, thank you. We would like to thank you all for taking time out of your busy schedules to attend this Chase Plastics Chase the Knowledge webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly, and her information is still posted here on your screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar in August. Have a great day.